Welcome everyone to this educational program brought to you by the Light Brigade and hosted by Lightwave Online. My name is Jerry Renville and I'm a senior instructor with the Light Brigade. First I want to thank Stephen Hardy and his entire team for making this platform available to us. This is the 17th in a series of webinars that are based on our comprehensive fiber optic training programs, and we hope they enlighten you about key topics and concerns within the industry today. Today, your speaker is me, Jerry Renville. Now, before I get started, I have a few housekeeping items I'd like to get out of the way. First, for your convenience, this presentation will be available on demand within 24 hours after we conclude today. We'll send a reminder email message to everyone who registered with a link to the archive once it's available. And the archive version of this webcast will also be accessible from the webcast archive section of the Lightwave website, which you can reach via their homepage at www.lightwaveonline.com. Since I like these broadcasts or webcasts to be interactive, I encourage you to ask questions at any time during today's event. You can forward these questions to me using the Ask a Question box that you should see on the left-hand side of your screen. All you have to do is click on the open area, type your question, and then click the submission button to send your question along. However, please note that I plan on holding off on answering your questions until I've concluded my presentation. And while I will be able to identify where the questions are coming from, I don't plan on revealing the identity of the Q&A participants. So you can feel free to ask a question while maintaining your anonymity if that's important to you. Also, if you have a tech support issue, you can alert us through this question box as well. One of the most commonly asked questions is whether a copy of this presentation is available for download. We do not make the PowerPoint presentations available for download. It contains a lot of proprietary material we use in our classroom courses, therefore we do not make it available. But you can always go to the Lightwave Online educational webpage and view the presentation in its entirety on demand as often as you want. And with that, let's begin. Now, the Light Brigade was founded in 1986, and over the course of that time, we have trained over 50,000 people in fiber optics since 1987. Our strengths are within our staff who come from various industries within the fiber optics field. The content that we use within our courses, the equipment is up to date, and the experience of our instructors is vast. We are a technology-based company, so we do not teach you how to use specific OTDRs, for example, but rather the concepts around the equipment as such. Now, the purpose of this webinar is to discuss some common misconceptions for fiber length versus cable length. For example, why is there a difference? What is excess fiber length, and how accurate is the sheath marking on a cable? What the term helix factor or lay length has to do with this, how the index of refraction or the cable index of refraction are different, and what happens if two spans of a fiber has different fiber manufacturers. We'll look at the types of faults that are frequently encountered, what can be done to provide accurate measurements for fault locations, and we'll also look at dead zones, data points, and the OTDRs themselves. Now, one of the things I looked into recently was a LinkedIn discussion page where this issue was recently addressed. Some of the answers that were provided were, for example, the optical length is always the same as the actual cable length. If we test cables, we use OTDRs to test the length of the fiber, and then we will check it with the cable length. If some little length gaps exist, it's normal. These are, again, misconceptions. For example, divide sheath footage by OTDR footage for the helix factor. It's actually close, but it's the other way around, and we'll discuss that during the webinar. Another response was, I have always been told 10% for wrap, a general number based on information from other splicers back in the day. That number is a little large. Actually, it's quite a bit large compared to what we'll see here during the webinar. Trace results, length measurements of a single fiber tested at different wavelength settings in your OTDR, from my observation, differs slightly in result readings. So your laser analysis is the same as the cable length, no difference from my perspective. Again, a misconception. And the last one that I noticed that was of note was the refractive index number provided by the cable manufacturer set on the OTDR will give the cable length. And generally speaking, that is incorrect. So what causes some of the length differences? A couple of terms we're going to introduce you to or reacquaint you with are the excess fiber length that is introduced in the buffer tubes. You can see in the drawing here on this slide that we have an optical fiber with an excess buffer length inside of the loose buffered cable. Again, this generally applies to outside plant conditions. The fiber has an excess length to allow for expansion and contraction of the cable during installation, cold temperatures, other examples like that. You'll also notice a difference in the inner and outer rows of buffer tubes. So we've got a picture of a fiber optic cable with inner and outer rows of buffer tubes on the right-hand side here. And you'll notice that there is a bit of a wrap from the individual buffer tubes there. Imagine taking a piece of string and wrapping it around the length of your finger. The string would represent the buffer tubes or the fiber length, and the finger would represent the central strength member or the cable length itself. If you were to unwrap that finger or string around your finger, you would notice that there is a bit of a difference between the two lengths. So, for example, in some of the outer rows, we'll discuss and look at some numbers here, but the difference can be as much as 4.9% between the actual fiber length and the cable itself. Here's a shot of a reverse helical wrap of a buffer tube, and showing what we call the switchback or the reverse oscillation point. Now, on a low fiber count cable like this, you may find that your fiber length versus your cable length can be as low as 1.6 to 1.8%. Again, the best way to get these exact numbers for your cable would be to call the cable manufacturer. However, you will notice that varying fiber counts will have differing lengths between the fiber and the cable themselves. Other factors that account for the length difference between the fiber and the cable could be, for example, sequential marking accuracy. In fact, it's not uncommon, it's not very common, but it's not uncommon that the cable may actually be longer than the sheath markings indicate. And we'll take a look at those numbers I got from a couple manufacturers here in a little bit. Also, the cable contraction in cold weather can be as much as 0.1 to 0.2%. You're talking to a person that is, or listening to a person that comes from Minnesota, and in the cold weather in January and February, you can have quite a bit of contraction. That might not seem like a big number, 0.1 to 0.2%, but for example, here on a 10,000-foot cable, this could be up to a 10 to 20-foot error. Other issues are going to be OTDR accuracy, concerning its clock accuracy, the data point spacing that you select, and the index of refraction variations in the fiber itself due to the mode field diameter and the wavelength. We'll also look at those factors as well. Now, excess fiber length, or EFL, is the difference between fiber length and the buffer tube that it is housed in. It is not the helical wrap or the helix factor. It's just the excess fiber that is in the buffer tubes themselves. Excess fiber length can add around 0.8% difference between the cable sheath and the fiber length, and is going to be slightly larger in some of the dry block cables that we currently see being installed today. As far as sheath marking accuracy goes, the sheath marking accuracy from a typical cable can be anywhere from 0 to plus 1%. In other words, the cable markings, the cable can be longer than the sheath markings indicate, but would never be shorter, to ensure that we get the length that we need at least. If we take a quick look into the helix factor here, we're going to find there are many reasons why the fibers in a buffer tube are wrapped helically around the strength member. One of the reasons is the strength. Very much the same way that a rope is stronger than an individual strand, the helical wrap gives the fiber optic cable a little bit more pull strength. The other is to help keep the cable round. Helical wrap helps keep the cable stay round while pulling through bends or tight corners. This would minimize the stress that can create micro cracks on the surface of the glass, which again can lead to failure. And the lay length along the cable needed for the fiber or buffer tube to wrap completely around the cable itself is the definition of that term. The helix factor creates an excess fiber length of, an excess length of fiber compared to the cable jacket, and unfortunately has, or fortunately, depending on how you look at it, has many different variables. So what are those variables? Well, the helix factor can vary with cable count, the number of layers of tubes, and the cable type. For example, a standard loose tube cable versus an all-dielectric self-supporting cable can have different helix factor values. The helix factor for fiber counts on cables up to 60 fibers on a standard loose tube cable from some of the manufacturers I spoke with can vary from 1.6 to 1.8%. If you go to larger count cables of 144 fibers with a single layer of buffer tubes, and I found some of the values to be around 3.8%. With inner and outer rows of buffer tubes, like the one we saw in the image in the earlier slide, the buffer tubes can be anywhere from 2.4 to 3.8% on the inner row and 3.8 to 4.9% on the outer rows, and which leads to another interesting fact that your two fiber lengths, or you can actually have two different fiber lengths within the same cable itself, and those need to be taken into account when troubleshooting or trying to locate faults. Now remember, the helix factor and the EFL are independent of one another and additive to the total fiber length. So why is this important? Well, faults. Trying to maintain service in a network is going to be critical if we have faults, locating them and repairing them. Some of the types of examples you can see here in this image and the next slide would be a complete cut of the cable. The old joke in the industry is to drive out and look for the fresh dirt, but again, we'll probably be better off using an OTDR. Sometimes you have partial damage to the cable, but not necessarily to the fiber itself, which could lead to faults later on down the road. Some examples of high fiber attenuation due to stress points, whether they are in the splice closures or direct buried cable or aerial attachments, can also lead to problems within our network. And on rare occasions, an open fiber in an undamaged cable is going to be absolutely critical that we have our OTDR set to the most accurate measurements possible. So here's an example of some other frequently encountered problems. If it's an intelligent transportation system and a vehicle gets off course, parallel construction, digging in yards can affect the cables. Rodents are a big fan of cables, as well as gunshot damage and other aerial factors such as ice loading, winds, trees and branches. These are just some of the frequently encountered problems we can run into. So what is the index of refraction? Well, by definition, the index of refraction is the ratio of the speed of light in a vacuum compared to the speed of light in the fiber. So, for example, if you go back to your 5th grade science class, you may have learned that the speed of light in a vacuum is 186,291 miles per second, or 299,792 kilometers per second, depending on which length of measurement you would use. Compared to the speed of light going through the glass, for example, if I had a fiber with an index of refraction of 1.471, the actual speed of light through that glass is going to be about 126,642 miles per second. Or perhaps another way to look at it is, if light can travel 186,291 miles per second in a vacuum, it would take 1.471 seconds to travel that same 186,291 miles. Now, keep in mind, again, the OTDR measures fiber length and not cable length. What do we mean by that? Well, if you look at a typical spec sheet from a cable manufacturer, refraction very commonly listed for both 1310 as well as 1550 nanometers. But that index of refraction value represents fiber and not necessarily the cable. Now, we just went through a little discussion here of why the fiber is different in length than the cable, and so that's what we're trying to say here when we talk about the OTDR measuring fiber length and not cable length. If you use those numbers from the cable manufacturers, your OTDR will be measuring fiber length. The manufacturer's index of refraction value is for the fiber and does not accurately match cable length like we previously discussed. So how do we do this? Well, one of the ways to accurately calibrate the OTDR, the technician must know the fiber size, the type of fiber, the manufacturer of the glass, as well as the wavelength that we're going to be testing at. And we'll look at those a little more in depth here in the next few slides coming along. So So testing with the wrong index of refraction, or what I like to call this page, missed it by that much. The correct index of refraction, which matches the cable sequential markings, must be entered into the OTDR for distances to be correct. Now, I'm just using an example of the index of refraction I'd stated earlier of 1.471, and this little table here will take a look at what the variations that will occur if we used a different index of refraction. For example, if I used an index of refraction of 1.472, a difference of 1/1000th in our ratio here, over a 10-kilometer span, my length measurement would be off by 6.8 meters, or almost 23 feet. That error is even greater magnified if we use an index of refraction that is even further away from the actual value we should be using. For example, an index of refraction of 1.481 over that same 10-kilometer span of cable, or 32,808 feet, would create an error of 68 meters, or 223 feet. The problem with this, too, is that these errors tend to multiply. So the longer my cable spans are, the greater the error becomes. That same 1.481 index of refraction that we used in our OTDR, for example, here on a 30-kilometer span, or 100,000-foot roughly span, would give us an error of over 200 meters, or almost 700 feet from where the actual fault might be located. I went through and discussed with some of the manufacturers, Corning, OFS, Draka, and got some index of refraction values from them, from their websites. And this is just kind of a list of some of those index of refraction values. See, for example, Corning has an index of refraction of 1.467 for their SMF 28E plus, 1.4677 for the SMF 28E. And if you have an older fiber plant, 1.4677 for the original SMF 28. Corning leaf fiber, you'll notice, does not have an index of refraction value for 1310, as most often the cutoff wavelength of this fiber is going to be above that value, so it wouldn't be a single mode wavelength that we would use. Again, the numbers are similar if you go to OFS and Draka and whatnot, but there are some slight variations, and this is why it's so critical to know which type of fiber is within our cable. One of the things I talk about with my students in our FO123 class is there are a handful of manufacturers of optical fiber glass itself and many manufacturers of optical fiber cable. So it's important that we know not only who the cable manufacturer is, but also whose glass, if you will, are they using within there. So, index of refraction, where do those numbers come from? Where does that 1.467 or 4682 or 4677, those numbers that we saw on the previous slide, what are those numbers? And those are approximations for a particular wavelength. So if you look here, for example, we have an index of refraction variation that's based on the different wavelengths. Now, some of the newer generation systems in fiber optics are using wavelengths such as 1490 is a common wavelength used in fiber to the home. 1577 is another wavelength being discussed in future PON systems, as well as 1610, 1625, or 1650. Typical OTDRs probably will have wavelengths of 1310 and 1550 and maybe 1625, depending on the machine that you purchased. One of the things to keep in mind is that as long as the wavelength that we're testing at is within 50 nanometers of the selected index of refraction, the difference in length value is going to be considered negligible. But you do want to keep that in mind, that the index of refraction does vary with wavelength. Another interesting aspect about the index of refraction is its variation due to the mode field diameter. Now, the mode field diameter is the distribution of power intensity across the end face of a single mode fiber. Basically, it's the beam of light compared to the size of the core. Typical mode field diameter here in this slide, courtesy of Corning Fiber with their SMF 28E+, shows that changes in the mode field diameter can affect the index of refraction as well. So a mode field diameter of 9 microns, for example, on this chart has an index of refraction value of 1.4679 at 1310 nanometers. The mode field diameter of 9.5 microns has an index of refraction value of 1.4675. Now, depending on which value you used, over a 10-kilometer span of fiber, the 1.4679 versus 1.4675 could be almost a 3-meter difference, or 10 feet roughly. So, again, if you look at the Corning specification sheets for their SMF-28E+, they will list their mode field diameter at 1,310 nanometers as 9.2 microns plus or minus 0.4. Again, I'm not trying to emphasize that we need to have the exact number or know the exact mode field diameter, but we do need to keep in mind that this will affect the accuracy of our measurement. So, how accurate is my OTDR, I guess, would be the next question. Since I've been involved in the fiber optic industry, we've gone from 40-pound mainframe OTDRs that use cathode ray tube displays to little handheld OTDRs that aren't much bigger than a cell phone at times, it seems. All of these OTDRs have a certain amount of what we call distance uncertainty involved with them. 3 of the factors that would contribute to this would be clock accuracy and stability. Your sampling resolution, or how many data points you select on your machine, as well as the index of refractions due to the mode field diameter and wavelength that I discussed earlier. Again, when you look at the wavelength of an OTDR, it might say that it's at 1,310 nanometers or 1,550 nanometers, but there can be a variation of plus or minus 15 to 25 nanometers to the actual wavelength of the laser that machine is using. So these values are often combined in a spec sheet if you look at an OTDR as the distance measurement accuracy or the distance uncertainty values, and that's what you would want to look for. A quick research of some of the various OTDRs on the market in terms of clock accuracy or the time domain of the OTDR capabilities, we noticed that they did vary from machine to machine and can range quite a bit. Some of the values noted on a quick comparison were anywhere from 0.0011% up to as much as 0.005%. Now, while these numbers may seem small, again, over a longer span of 40 kilometers or so, we would still see a 2-meter error. And a lot of times I hear people say, or in my classes will ask me, well, 2 meters, that's actually pretty close over a 40-kilometer span, isn't it? And yes, it is, but my response often to the students then is, but what about if you're the guy with the shovel? Another thing we need to look at with the OTDR itself is data points or sampling resolution. I've had a little slide here shown up with 2 OTDR traces of the same fiber using different sampling values or data points. Now, how does this reflect accuracy? With the little X's that you see on the top trace and the ones that you see on below, those represent the data points. And the typical sampling resolution of those values can be anywhere from 0.04 meters all the way up to 5 meters. This is a value that you are able to select as you set up your OTDR for testing. On some of the handhelds, I've seen the data point selection as many as 30,000 data points that can be selected, and then on your higher-end OTDRs, up to as many as 256,000 data points. So if you look at the variation between those two numbers, here I have a trace with a cut cable, and my OTDR that has a fewer sampling resolution or fewer data points, if you will, is showing me that the fault might not be exactly where it is in reality. So that's something we need to keep in mind for longer distances is how many data points are we actually using. Another consideration that we like to take into account is the OTDR dead zone itself here. I've created a little slide drawing, if you will, of a OTDR trace with a cut cable. And the cut is somewhere near a cross-connect panel. Now, because of the reflection created by that connector in that panel, we're going to create a dead zone which may or may not hide where the actual fault is. It could be right in the cross-connect panel, or it could be as much as 5, 10, 50 meters away, depending again on what the pulse width is used. Some of the factors that can affect the dead zone, for example, are the pulse width setting that we select, and those are typically listed in time values from nanoseconds up to microseconds, and occasionally they might be listed as a distance in terms of meters. The reflection of the front panel connector or the connector that we're looking at, and also the detector circuitry, or how fast can that detector recover from these blinding reflective events. Keep in mind, the shorter the laser pulse, the shorter the dead zone. Unfortunately, the shorter the pulse width, the less clean, if you will, the trace will look. So it's kind of a balancing act between having a short pulse width to create small dead zones and yet a long enough pulse width to create a clean trace that you'll find yourself having to choose between. So again, I pose the question in this slide here, is the break within the panel or is it beyond? The dead zone is hiding that information from us, and it's something that we should really need to keep in mind when we're trying to locate faults. Another example here that could be affected by the OTDR accuracy or fault location itself is a fiber roll-off. Now, this is often caused by a non-reflective event at the fiber end. If you're familiar with an OTDR trace, you'd notice that most OTDR traces are going to give me a reflective or a Fresnel spike at the end of the fiber due to the glass-air interface that's creating that reflection. However, a jagged break, an extreme macro bend, perhaps the cable is cut and laying in water, or if the cable gel has gotten over the end of the fiber, you might not be able to find that Fresnel reflection, which again could make locating a little more difficult. If you have a roll-off, my suggestion would be to shoot another fiber to see if possibly we can find the end that does produce a Fresnel reflection so we can more accurately state where this fault is located. Now here we have a cable span with more than one index of refraction. So which value do we use here? So example, we have a cable index of refraction in section 1 that maybe was initially installed of a value of 1.507. Later on, we might have added a new section of cable to extend the reach of this original plant, and this cable has an index of refraction of 1.512. In the top example, I list an example of using the initial 1.507 cable index of refraction, and you'll notice on the slide itself that it shows the 2 points that I'm measuring from. A marker A, for example, of 3,796 meters would be accurate. However, marker B, because that section of cable has a different cable index of refraction, that number would be incorrect. So therefore, the distance from A to B that you'll notice on the right-hand side of 2,300 meters is not going to be correct. So the one that may not be as obvious to us is basically we want to use the cable index of refraction in the section of cable where we're interested in locating the fault. And in this case, it's in section 2. Well, how does that happen? If I use cable index of refraction value of 1.512, my marker A at 3,783 meters, as well as marker B of 6,075 meters, are both incorrect values. In other words, those aren't the actual distances that we're looking at. Fortunately for us, the difference between marker A and marker B is accurate because the distance between them would in fact be 2,292 meters. Again, an 8-meter difference in an example like this. 25 feet when repairing and restoring is of the utmost importance. This is a factor that we definitely want to take a look at. So another interesting fact, and we'll cover it a little bit more later too, is you'll notice that I am not actually measuring from the beginning or where the OTDR is located to the event that I'm interested in looking at, but rather I'm measuring from the closest known event to that fault. And the reason I do that is that the error of 1% or 2% or whatever that value is not going to be as great if the distance from the two events, in this case marker A to B, is shorter than the actual distance to marker B. I hope I didn't make that too confusing, but if I did, please ask a question in the Ask a Question box, and we'll try to address that more in depth for you. So one of the best times to find out what the cable index of refraction is going to be for the cable that we're installing would be during the acceptance test here. Here we have a gentleman who's doing an OTDR acceptance test of a fiber optic cable. You'll notice that he's using a short little pigtail with a reusable mechanical splice. The fiber optics acceptance testing ensures that any new cable matches the optical and physical requirements of the planned application. And also the testing should be performed upon delivery of the cable prior to its installation. Basically, if there are any faults, which are not likely but possible, we'd like to find them then. And then we can also take some time to calibrate the OTDR to have the OTDR trace match the sheath markings or the sequential markings of the cable itself. It's a little more difficult to do once the cable's installed. So how do we do that? Well, to determine the cable index of refraction, like I said, is another reason to acceptance test the cable prior to installation. And keep in mind, as we stated earlier, loose buffered cables will have a difference between sheath length and actual fiber length, and all the other factors that we discussed as well. So we test the cable using the correct fiber index of refraction for each fiber. Compare the results to the sequential markings on the cable tested, and then this following equation would help us determine what the exact cable helix factor would be. So in this example I've thrown up here, I have a helix factor that is equal to the fiber length divided by the sheath length. With my test with the OTDR, if I have a fiber length trace of 10,320 feet, and I have a sequential marking or sheath length of 10,000 feet, we come up with a number of 1.032, or a helix factor of 3.2%. This number can be handy with some OTDRs that do have an input for the helix factor. However, most of the OTDRs that I've worked with in my experience do not have that value. So what I would simply do is take that number that I created or determined during my acceptance test and multiply it by the fiber index of refraction. So in this example here, we have a helix factor of 1.032 multiplied by the fiber index of refraction of 1.467 and a cable index of refraction value of 1.514. This is the number I would document if and when I had to do a restoration or a locate of a fault somewhere down the road. What else is involved with the OTDR portion of the acceptance test? Well, open one end of the cable and connect the OTDR via mechanical splice like we saw in the image earlier. Confirm the attenuation or the dB per kilometer for each wavelength. These values are going to vary, but we do have industry standards set for the different wavelengths. Verify the OTDR trace is linear. In other words, there are no events in the span. It should be a nice, flat, downward sloping trace. If we did have an event, that could indicate that the cable has been stressed or possibly not stored properly during shipping to us, whatever the case may be. Now, to ensure continuity throughout the cable, the technician may open the opposite end of the cable to access the fibers. And then while operating in real time, a macro band or an index matching gel on the far end will remove the reflective event. Verifying the cable is continuous throughout by witnessing the disappearance of that far end Fresnel reflection. It's very difficult to do a continuity test with an OTDR without this type of example that I explained because, again, the OTDR trace will go to the end of the fiber. If the end of the fiber is the end of the cable, then we're continuous, but we really can't verify that unless we actually are able to witness the Fresnel reflection disappearing at the far end. I've also included here just a quick example of an acceptance test form that we use here at the Light Brigade. We list the customer, the work order, the fiber type, the cable manufacturer, the index of refraction values that we'll be testing at, as well as the physical appearance of the cable. Are there any signs of damage on the jacket itself? And we'll take readings from the cable reel, mark the sequential markings from start to end, and then document the lengths measured at the appropriate wavelengths. So having a form like this is very handy, especially if you're going to be installing the cable. It does help us verify that, yes, we did have a good cable prior to installation. It's really handy if someone else is installing the cable for you. So as we get close to the end here, just a couple of more items in terms of how do we improve the accuracy in our restorations. As I'd mentioned earlier, always measure from the closest known location. Again, as an example, a 3% error that is 1 kilometer away is a much smaller one than one that is 10 kilometers away. And in this case, our accuracy would be within a factor of 10. If possible, another tip would be to measure from both ends, if the equipment and the manpower is available, of course. This could help pinpoint the damage and could also reveal multiple breaks. So testing from both ends, although somewhat problematic, is and can be very helpful. And then another tip that I would recommend is also to test at the higher wavelengths. For example, 1550 nanometers or 1625 if you have that capability on your OTDR. Not only will this help us reveal where the break is, but it will also reveal any stress points prior to the break and actually reveal the extent of the damage. For example, we had one instance where a cable was dug up with a backhoe. We located the break with the OTDR, but we also noticed that there was a considerable amount of length prior to the break that needed to be cut out because it was also damaged when the backhoe pulled the cable out of the ground. So in this example here on the illustrations that I provided at 1310 nanometers or 1550 nanometers, the dotted line that you see at the end of the trace would represent how long this span actually was. This is not going to show up on your OTDR if you were wondering that, but it gives us a comparison of where it was, and we can see the fault at the end there at 1310 nanometers. Now, when we test the same fault or the same span at 1550 nanometers, we can see that there's another event that's been added which could very well or is a stress point that the higher wavelength is picking up. And that's why it's always important to test it both wavelengths, both at the 1310 and the 1550, or at least two different wavelengths that are a considerable distance apart, because the higher the wavelength, the more susceptible or the greater the fault would be at any given point, and the lower wavelength gives me a comparison. So that kind of wraps it up for us. I hope you found this webinar useful. Again, we will open it up here very soon to some question and answers and go from there. A couple of things about the Light Brigade. We do have instructor-led hands-on training courses, our Fiber Optics 1, 2, 3 class, or advanced hands-on training. You can find the location of our classes and the dates by going to our website at www.lightbrigade.com. Perhaps if you're interested in a little more in-depth theory about the OTDR and its operation itself, we also have a wonderful DVD that's available for sale. In fact, you can get any Light Brigade DVD for just $99 each through October 10th with the code DVD99 at lightbrigade.com. And with that, we come to the end of our program today. We'll go ahead and look at some of the questions that we have. Okay, one of the questions we have, testing with the wrong index of refraction. What happens if the end-to-end OTDR test requires spans of multiple fiber types? Do we use the dominant value or the one with the most length, etc.? And I did address that in the discussion earlier, again, emphasizing that we want to use the index of refraction in the area that we are interested in or where the fault is located in that example. I hope that made sense to you. Another question we have is to test multi-mode at 1550 nanometer using a single mode OTDR with a mode conditioning lead. I'm going to have to take a little time. That's a little more in-depth of a question. I think that we have time here on the webinar, but I will certainly get back to you on that via email. I apologize for not directly answering it at this point. I have a feeling it's somewhat questions others would be interested in. It's just there's so many questions here. I want to get to as many as possible without spending too much time. About how much time can a dark fiber stay with the same characteristics? Does it suffer somehow because it's not used? Does it have any affectation because of staying dark a long time? That's a very interesting question that you bring up there, and it's something that I have not experienced myself. In other words, because a fiber is not allocated or used within the network, I have not experienced where something would change or suffer, as your question might indicate here. Perhaps you've seen something different, but as far as my experience, I've not noticed that. Can you recommend device for bare fiber testing connection to an OTDR? Okay, sorry about that. Can you recommend device for bare fiber testing connection to OTDR? One of the things I've always used over the years is a mechanical splice by a company called Norland, N-O-R-L-A-N-D. It's a glass rod with plastic inserts that is just a wonderful splice in terms of being able to use it many, many times. It has an index matching fluid that comes with it. I have not liked the bare fiber adapters or other options. I just find this one a little easier for me. Perhaps others have options that they use, but my preference is a mechanical splice with a pigtail. It's easier to replace and repair and whatnot. Another question we have is, does the Light Brigade calibrate OTDRs? And the short answer to that question would be no. It would not be a bad idea to every now and then get with the manufacturer of your OTDR and have it sent in for a clean and inspect and to have it take and look at. There was an interesting study that was done that showed that 90% of the OTDRs that came in for repairs was due to damaged connector end faces. So even though it doesn't really deal with the distance issue that this webinar is referring to, I think it is wise to make sure that we are always conscientious of cleaning our connectors or our pigtails before plugging into any test equipment. Okay. And then the final question, there are a few other questions. I think we'll wrap it up here with this last question. Does the size or length of the dead zone affect the accuracy of the total length of my span? The answer to that would be no. The size of the length of the dead zone would not affect the total length. It only affects events that might be hidden within the dead zone. So that's where the big concern would be in that respect. Remember, the data point can affect the total length, but the dead zone would not. So with that, we come to an end to our program today. If I didn't get a chance to answer your questions just now, or you're viewing this webcast from the archives, you can contact the Light Brigade directly via the Contact Us tab on our website at www.lightbrigade.com. As I mentioned at the start of this event, the archived version of this webcast will also be available or accessible from the Lightwave homepage at www.lightwaveonline.com. And with that, I'd like to thank everyone in our audience for your attention and interest. I hope you'll join us for our next webcast on October 29th when we discuss important concerns about establishing a fiber optic maintenance program. Until then, have a great day and goodbye.